In this module, you will be learning about preparative methods of metalloboranes. Literature abounds with synthetic methods giving high yields of metalloboranes. In metalloboranes, metals confer on clusters a flexibility of geometrical structure and chemical reactivity more than that of parent boranes themselves. The clusters are composed solely of metal and boron atoms as vertices containing direct metal bond connectivities. The pure metal boron clusters that are bonded exclusively or at least predominantly by MX-BY interactions influence geometrical structure, stability and chemical reactivity of these compounds. Let us see the general methods of preparation of metalloboranes. In view of the complexity of synthetic methods of metalloboranes, no simple classification can be described. However, the basis of classification is the type of metal containing reagent that is used, or the type of borane substrate involved, or the observed overall result of the reaction. The most general route involves the reaction of a mononuclear metal coordination complex with a borane anion or the parent borane. Simple metathesis may occur, or a more complex series of reactions may happen, like polyhepta coordination of metal center by the borane anion with or without the cluster rearrangement, oxidative insertion of metal center to give an expanded cluster, partial degradation of the borane anion itself or of the metalloborane intermediate to give metalloborane with fewer boron atoms in the cluster, or deprotonation of a preformed metalloborane to give a metalloborane anion, which can then be reacted with a metal complex to give either a homo or a hetero polymetalloborane. The following features are involved in the synthetic strategies. Firstly, the deprotonation of the borane is affected by a metal hydride such as sodium hydride or potassium hydride. Or we can also use bases such as metal alkyls like methyl lithium or butyl lithium, or more gently by the use of N-N-N-N- tetramethyl naphthalene 1,8-diamine, in short TMND, which is also popularly known as a proton sponge. It is an excellent Bronsted base, that is a proton acceptor, but a very weak nucleophile towards boron. Now, after having deprotonation of the borane anion, the synthesis can start with a anion such as clozo B10H10 2- or anido B9H12- or arachno B9H14, etc. These reactions occur rapidly in ethereal solutions or dichloromethyl solutions, either at room temperature or below room temperature. Let us study various methods of preparation one by one with examples, starting with simple metathesis of borane anion. In this method, the simple metathesis wherein the borane is deprotonated using a hydride base followed by a reaction with metal complex to give a metalloborane cluster. For example, in this reaction, B5H9 borane is treated with potassium hydride to give you the corresponding anion after the loss of a proton, that is B5H8-. This anion is then reacted with an iron complex such as shown here, eta 5 cyclopentadienyl dicarbonyl iodine iron, and this borane anion gets inserted into the coordination sphere of iron to give you a metalloborane cluster. Similarly, B5H9 after treatment with potassium hydride gets deprotonated to form B5H8-. This anion is treated with a copper complex such as tris triphenylphosphine chlorocopper to give you a copper metalloborane, wherein this borane atom, borane cluster gets inserted into the copper coordination sphere. The second method is the polyhepta coordination with or without cluster rearrangement. The polyhepta means coordination through more than one atoms as represented by eta. As you can see in the following examples, the borane anion replaces one or more ligands in the metal coordination sphere, and it is coordinated to the metal through more than one atom as represented by eta 4, eta 3, etc. Let us see the first reaction, wherein B10H14 is treated with TMND, that is tetramethylnaphthalene diamine, and a platinum complex to give you a platinum metalloborane, wherein the borane is attached to the platinum through 4 atoms as represented by eta 4. Similarly, in another example, B10H13Cl is treated with TMND and the cis platinum complex in benzene to give you 2 metalloboranes in 60% and 30% yield respectively. Another reaction wherein the NTB18H22 is treated with a cis platinum complex in the presence of a base to give you a platinum metalloborane, wherein this borane is attached to platinum either by eta 4 linkage or eta 4 and eta 2 linkage as shown in this complex. In yet another example, we have B3H8- reacted with platinum complex in presence of a base such as triethylamine to give you another platinum complex with borane, wherein the borane is attached to platinum through eta 3 linkage. Another way of preparation of metalloboranes is oxidative insertion of a metal to obtain an expanded cluster. As the name of the method suggests, there is an oxidation of the metal that is happening due to the insertion of borane. For example, B5H8- reacts with trans-iridium complex, wherein the B5H8 has replaced the chlorine atom and increased the oxidation state of iridium from +1 to +3 state. Similarly, in the second reaction also, this B3H8- has reacted with the iridium complex, increasing the oxidation state of iridium from +1 to +3 oxidation state, and thereby expanding the cluster. Another method wherein the partial degradation happens either of a borane anion or a metalloborane intermediate. In these reactions, partial degradation of borane leads to the formation of metalloboranes with lesser number of boron atoms in the metal coordination sphere as compared to the starting borane. Let us see in the first example, wherein we have started from B9H14- and reacted it with a cis platinum complex to give you an arachnometalloborane cluster. As you can note here, we started with B9 unit, and the borane which is attached to the metal coordination sphere has only 8 boron atoms, and hence it has undergone a partial degradation. Similarly, in the second reaction, you can see we started with B10H10-2- and reacted it with a trans-iridium complex to give you numerous metalloborane products containing 4 to 8 boron atoms. Similarly, when we started with B5H8- and reacted it with cobalt chloride and cyclopentadienyl anion in presence of THF, we got numerous metalloborane products containing 3, 4 or 9 boron atoms. So this constitutes the partial degradation of borane anion to form the metalloborane clusters. In yet another method, deprotonation of metalloborane plus its further metallation. In these reactions, the metalloborane cluster is treated with a hydride base, and after deprotonation, it is reacted with another metal complex to give a new metalloborane. For example, we started with the metalloborane having platinum metal atom and another platinum complex in presence of a base such as potassium hydride, and we have got a new metalloborane as shown in this reaction. In another example, we started with a nido complex of osmium with borane, and then it is treated with the base such as sodium hydride, followed by its reaction with a platinum complex, giving you a hetero metal cluster wherein we have both the osmium as well as platinum metal atoms. Another set of synthetic routes to metalloboranes involves the direct reaction of neutral borane with various reagents, wherein the borane can either act as a simple ligand, for example, as a simple electron pair donor or a Lewis base, or other reactions wherein the borane can act as a proton donor, that is, as Bronsted acid, or some other reactions in which borane can act as an oxidizing agent, or simply the source of borane cluster fragments. Let us see these examples one by one. The following examples quote borane as simple 2-electron donor. In this reaction, the nido B6H10 displaces other ligands from their metal complexes by acting itself as a Lewis base, that is a 2-electron donor. Let us look at this reaction wherein this nido B6H10 is reacted with iron carbonyl at room temperature to give you an iron metalloborane cluster wherein B6H10 has replaced the carbonyl groups and acted as 2-electron donor. Similarly, the nido B6H10 when reacted with a platinum complex at room temperature gave a metalloborane having platinum metal atom wherein this B6H10 is acting as a simple 2-electron donor. Let us see how borane is acting as a Bronsted acid. Boranes as Bronsted acids can be deprotonated by metal alkyls and other reagents to give a variety of metalloboranes. The reaction of B10H14 with cadmium diethyl in presence of diethyl ether gave a metalloborane with cadmium as the metal atom. As we can see that B10H14 has undergone a deprotonation by using diethyl cadmium as the base and the formation of the resultant metalloborane cluster. In the next reaction, the B10H14 with the electron rich complex niclosine in monoglyme or benzene for 1 hour yields a nido nickel borane complex, whereas the prolonged reaction yields a como nickel borane cluster as the main metalloborane product. Now, the example where borane plus a dispersed metal is used. The direct reaction of borane with finely dispersed metals such as zinc, cobalt or nickel can be regarded as involving decarborane either as an acid or an oxidizing agent. For example, the B4H14 with metal which is dispersed gives you a como metalloborane cluster as shown here. Another example where borane adds to atomized metal. The atomized metals, particularly in the presence of ligands, can be used to give a mixture of polymetalloboranes. However, they are produced in low yields. For example, B5H9 when reacts with atomic cobalt in presence of cyclopentadiene gives you a metalloborane cluster having cobalt as the metal atom plus other products, thereby decreasing the yield of the metalloborane cluster. In a more general method, the oxidative addition of BH bond to iridium. This reaction affords a good yield of certain sigma bonded metalloboranes but appears not to be very general. For example, B5H9 when react with a trans complex of iridium gives you a nido-iridium metalloborane as shown in the following reaction. Another example is cluster expansion by using diborane. In this case, the metalloborane anion acts as an electron pair donor to the acceptor, which is BH3. The treatment of the product with anhydrous HCl at minus 110 degrees Celsius yields 1 mole of hydrogen gas and a neutral metalloborane, that is Fe eta 2 B7 H11 tetracarbonyl. Yet another way is synthesis of small clusters from mononuclear units. The monoborane reagent, that is BH3.THF, can be used to generate a small metalloborane cluster from the mononuclear units, that is tetracarbonyl iron and BH3.THF. This seems to be a very simple method which provides high yield. Co-thermolysis of a borane with metal carbonyl. The co-thermolysis of a borane with metal carbonyl or related metal complex yields product which is having only not more than 20% yields. However, by modifying the reaction conditions, the yield can be improved. For example, as shown here, B5H9 when reacts with iron carbonyl at 220 degrees and the reaction is quenched, we get nido 222 tricarbonyl 2Fe B5H9. However, when the same reaction is allowed for a prolonged period of time, the product obtained is nido 111 pentacarbonyl 1 Fe B4H8. The similar reagents when reacted in presence of polyether and lithium aluminium hydride at 60 degrees gives nido 111 222 hexacarbonyl 12 Fe2 B3H7. Similarly, with cobalt complexes, when B5H9 is reacted with the following cobalt complex at 225 degrees Celsius, it provides nido 1 eta 5 C5H5 1 cobalt B5H9 plus other products. In another method of preparation of metalloboranes, we have anodic dissolution of metals in the presence of borane anion and appropriate ligands. For example, the electrolysis of copper serving as anode with B3H8- in presence of triphenyl phosphine gives you a metalloborane with copper as the metal. In yet another example of cluster expansion during the reaction of a borane anion with a metal halide in the presence of a ligand as shown in the following example. Sodium B5H8, that is a borane anion, when react with nickel dibromide, a metal halide, in presence of cyclopentadienyl anion gives a clozo-metalloborane complex 1,6 eta 5 C5H5 whole twice 1,6 nickel 2 B8H8 plus a clozo 1,7 eta 5 C5H5 whole twice 1,7 nickel 2 B10 H10. Similarly, NaB5H8, that is B5H8 minus, reacts with bis cyclopentadienyl nickel in THF in the presence of stoichiometric amounts of sodium amalgam to give up to 17% of clozo 1278 eta 5 C5H5 whole 24 1278 nickel 4 B4H4 and 10% of nido 1678 eta 5 C5H5 whole 24 1678 nickel 4 B5H5. Now let us summarize what are the different methods of preparation of metalloboranes that we have learned. We have learned a simple metathesis of borane anion for the preparation of metalloborane clusters. We have seen the polyhepta coordination wherein the boranes are attached to the metal atoms with more than one atoms with or without the cluster rearrangement. We have also learned the oxidative insertion of a metal to obtain an expanded cluster, wherein the insertion of borane to the metal coordination sphere leads to increase in the oxidation state of the central metal atom. We have also learned the partial degradation of a borane anion or the metalloborane intermediate, wherein we get the metalloboranes with lesser number of boron atoms in the coordination sphere. We have learned the deprotonation of a metalloborane plus further metallation, which gives you more complex metalloborane clusters, and we can have different metal ions or different metal atoms in the coordination sphere. We can have either homo or heterometalloclusters. We have learned co-thermolysis of a borane with a metal carbonyl. We have also learned the anodic dissolution of metals in presence of a borane anion and appropriate ligands to get the required metalloborane clusters. We have also learned the cluster expansion during the reaction of a borane anion with a metal halide in presence of a ligand.